So I'll tell you a little bit more about that. First of all, I want to tell you that most of the work I'm showing, it's not only my work, it's a work of a large group of people. We're dedicated to creating virtual humans for healthcare applications. So, as I mentioned before, ELEM Biotech is a spinoff from the Barcelona Supercomputing Center. And in that picture, you can see the old Mare Nostrum 4. This is a supercomputer in Barcelona that it's the only supercomputer located inside a chapel. So it was quite unique. Currently, the new supercomputer is not located there. However, the new quantum computer will be located there. So that's going to be quite exciting. Now, as a spin-off from the Barcelona supercomputer, what we want to do is to use all of our computational models or of our computational tools to create in silico trials and personalized solutions in healthcare. We use both mechanistic and AI modeling from the cell to the organ level. Which is, quite what you mostly have been learning potentially in this course. And I'll tell you more about what we do in that area. And we have all of these technologies that were created for the use in supercomputers, but we can now also deploy in cloud infrastructures. So that is also one key of our technology. So in terms of when you try to model a human, it's a huge computational challenge. It's a huge technical challenge. To recreate biological systems, it's quite complex. The more complex a system, potentially the more detail you would like to add to that simulation. Many times you need larger computers for that. When you have large computers, you actually have to create quite efficient code to be able to exploit that supercomputing infrastructure and actually run large scale simulations. So that's one of the key things about coming from the Barcelona Supercomputing Center. The code that we employ is called Alya. And it was fully created in-house there at the Barcelona Supercomputing Center to be able and designed specifically to be able to run in supercomputers. So, as you know, currently, and there has been a big push by regulatory agencies and by industry as well to try to use modeling and simulation to actually speed up and create more efficient regulatory pathways for drugs, for devices, for all healthcare needs. And this was particularly visible or seen during the COVID pandemic, where we figured out that we needed to find approaches that were faster. And that could test things in a highly reliable way, and so that they could be delivered faster where they were needed. So this is where we are actually, that's the area where we're trying to cover right now, including more of the virtual patients in this pipeline. So at ELEM, what we have been doing is to create a virtual humans platform. What we have been employing, as I mentioned before, is the supercomputing efficiency of our code, Alya, where we do multi-scale and multi-physics modeling. Actually, that code is not only used for healthcare, it's used for many, many different applications in aerospace, in combustion, in loads of different areas where you can use high fidelity multi-physics finite element modeling codes. So with this code, we actually can also help us to reproduce virtual populations. And for that, of course, there are different pipelines where you can create different virtual populations so that you can solve them. The whole idea is to be able to have a platform where you can perform in silico clinical trials, and you can optimize and personalize different medical therapies. So, everyone, I think, right now is very keen on using in silico clinical trials, and there are many reasons why. Within in silico trials, you can actually inform decision making. This is an example in drug discovery and drug development. They have become quite interesting and useful to be able to provide information about human physiology even before you go into humans. So that is quite helpful. You can target different therapeutic areas, and the area that I'll be talking the most is cardiac, in the cardiac safety, because that's my main area of expertise, and second, that's the main area where ELEM has done the biggest advances in this sense. So within silico clinical trials, you can actually discard unsafe molecules very fast. You can quantify risks to a human population from the first day you have a molecule and you want to try to see whether it could have a risk further up in the development pipeline. So that is quite interesting. So you can also ease the translation from animals to humans. As you have probably heard, many of these models have actually provided a better translation value than animal models. We know that animal models have been very valuable for understanding physiology. However, when it comes to translation to human, it is very difficult to reproduce both human pathology in an animal and for the animal to respond in the same mechanism as the human when you're actually treating it or something. So mathematical modeling has become quite an important area in this sense. You can also perform unlimited clinical trials. Actually, this is quite important in terms of ethical concerns, because then you can actually study and target perhaps populations that are vulnerable, or patients that are vulnerable, and you may want to know beforehand what their potential response would be to a therapy before you put them through that. So it actually eases a lot part of the ethical issues when you're talking about healthcare. Of course, it comes with more questions about that, because not all model is perfect, but that comes in how you're designing the model and what is the exact context of use and purpose of that model. Now, you can produce large-scale scientific evidence because you can create as many simulations as you want. You can create hundreds, thousands of simulations, and you can produce evidence in those hundreds or thousands of virtual humans. That is also valuable because then you can actually study the differences and different, specific characteristics of these populations and how they influence on that specific therapy or pathology you're studying. You're minimizing the risks, of course, because you provide information early on the stages of device or drug development. You can enable these long-term studies because you can also have an extended population and potentially try to observe how those populations may be changing over time. And one of the key issues as well that we're trying to tackle is that you want to create different cohorts with different ages, different sex, different hormonal stages, different pathologies, so that you can actually understand what a single therapy would be, how it could be affecting, other cohorts of populations, and you can actually stratify potentially better your therapy. So this high ability to create these virtual patients and to analyze drugs and to create populations actually provides us with the ability to be a potential digital CRO as well. Because basically any industry, from the pharmaceutical industry or the device industry, could potentially come to use some of the platforms that we are creating and select the kind of population that they want, select the different subjects that they want to test, and perform all of their assays or all of their tests on those populations, and receive their results already, in a highly processed, in a very, very fast way. So basically, what would take a clinical trial that takes months or potentially even years, if you're talking about a rare disease, you can get results from computational evidence within a few weeks, a week or two, or a few weeks. So that is why I think in silico trials is part of the future of testing and regulatory of the future also of evidence, adding more evidence to the regulatory pathways to have safer, faster, and potentially also cheaper drugs and devices. So I'm going to talk to you a little bit more about the human heart, as well as I mentioned before. This is where I've worked most of the time. And, from the physics point of view, we have the heart as three different specific physics: the electrophysiology, the mechanics, and the blood flow. And each of them can be solved with different models and with different methodologies. Of course, it depends on the specific needs for your simulation. You can have purely electrophysiology models. You can have electromechanic models, and you can have either a full solution of the blood flow with Newtonian physics or Newtonian mechanics. Or provide other more simplified models of blood flow if you're mostly interested in the electrophysiology and mechanics. And it also depends on the extent of the blood flow or the arterial system that you want to model. These are some of the models that we run, very frequently. The typical, you've probably heard about it, the O'Hare-Rudy model. This is a more simplified model. Rogers-McCulloch, Courtemanche for the atria. In terms of the mechanics, we have the solid mechanics of Holzapfel and Ogden that was published a while ago. Excitation contraction coupling of land. And of course, in terms of the blood flow, we can solve Newtonian blood flow using also arbitrary Lagrangian Eulerian methods for the coupling of the mechanics and the blood flow. That's tightly coupled, and also inverse boundary, depending on the kind of problem that we're talking about. So the one model that we use on I would say almost every day is a model where we do not have the entire fluid-solid interaction as such, but we model the hemodynamics using a zero-D closed-loop model, where we can have the effect of the entire arterial network in an approximate manner, and actually model this arterioventricular coupling. That is actually quite important to actually be able to capture the effects of any changes on your electrophysiology or on the mechanics of your heart, and be able to understand how that actually affects the entire network. Now, this is one example of one of our simulations. This heart comes from a healthy volunteer. And you can see, it's colored by the electrophysiology activation. And we have all of the pressure and volume information of the right ventricle, of the left ventricle, and a pseudo ECG. So you can compute some of the pressure volume loops, and you can observe the entire, approximate function. It's something quite interesting of our models of ELEM is that every employee, if you want to, you can get your heart scanned. And we have actually a cohort of our own hearts, which we can use and work on, for any kind of project or any kind of specific purpose. So it's quite nice and interesting. I have my own heart. Actually, my own heart is displayed at the London Science Museum, if you ever stop by. And it's something quite nice and neat for us to work on. So we also, as I showed you before, it's the hearts when we let me just go back. When we obtain our own hearts from cardiac MRI, it is very difficult, since they're in motion, it is very difficult to actually capture all of the endocardial detail. I mean, our hearts are never this nice and smooth. They have a lot of papillary muscle. Well, they have papillary muscles. They have a lot of trabeculae. They have false tendons. They have a lot of different tissues here inside that actually help the heart pump in a very efficient manner. That's their main purpose. But when we capture that from our own scans, it is very difficult to capture. We do not have enough resolution, mostly because of motion. We cannot actually capture them. So some of the studies that we did at the very, some while ago, was to actually look at patients. These are as a large cohort of explanted donor hearts that were not able to either they were not able to be implanted in someone else, or they just couldn't make it. So there is a large database from the University of Minnesota in the Visible Heart Laboratory, with whom we have been working for a good amount of time, where we were able to obtain some of these hearts. Not the hearts, but they had done high resolution imaging from those hearts. And you can actually observe all of the different trabeculae and papillaries, and how different they are between hearts. So with that, what we have been doing is actually to use these hearts to try to understand a little bit better what are we missing when we simulate all of these hearts without all of these different muscles. And of course, we have this for different patients, for different donors with heart disease and without heart disease, for male, females, children. And from those data sets, we have also been able to create methodologies to extend them into large patient databases. So basically, with pipelines for creating virtual populations, using different kinds of methodologies, we can actually expand this and do hundreds and thousands of hearts, which is quite interesting. Now, of course, what we can do with these technologies, we try to apply them again, not only to the healthy scenarios, but to also to disease scenarios, where we can try to model things like ischemia, heart failure, hypertension, as I mentioned, because you can also modify the 0D model of the circulatory system to provide conditions like hypertension, like aortic stenosis, and you can actually observe what is the response of the heart, specifically here the pressure-volume relationships inside the left ventricle that are affected by these external factors. So, this is probably, these are things that you have probably seen before, but I'll go a little bit deep in certain scenarios, not on everything. So this is, for example, also a case of patient hearts as well with myocardial infarction, where we can actually, capture the myocardial infarction within this anatomy for the deep scar and the border zone, and we can actually use it to simulate the mechanics of that heart and try to observe what is actually the effect of that scar in that heart, how it's actually reducing, and changing my pressure-volume relationships, and observe different strains actually, and how the strain is affected by that specific infarction. Now, the nice thing also is this, for example, here we can actually observe the hemodynamic effects of a ventricular tachycardia. So this specific patient went for an ablation because of a ventricular tachycardia. And here we're actually, simulating that tachycardia and looking at how it actually affects that hemodynamics of that patient. Of course, it becomes variable. It becomes, more difficult to procure blood to the rest of the body while you're having that tachycardia. Of course, some of these methodologies can also be applied to different other pathologies. In this case, we're trying to model obstructive hypertrophic cardiomyopathy, where you have this big bulge in the septum that actually obstructs the outflow. So, of course, you need to take into account the fiber disarray, and you can assess how different approximations of or percentages of fiber disarray can produce and can change the mechanics of your problem. Other work where we have been doing, of course, apply this to the human atria, where we're actually also trying to model the electromechanics of the human atria and reproduce some of the hemodynamics because of its contraction. This is actually very interesting to try to model as well atrial fibrillation and potentially the effects of drugs as well on atrial fibrillation and on different aspects of atrial pathology. Now, in the atria, this is more newer results. We haven't applied as much of drug testing on atria, but hopefully we'll be doing that very, very soon. So again, we want to be able to study the atrial fibrillation and to provide models of atrial fibrillation to any company, anyone who may require them to study any specific problem, either from the medical device area or from the drug development area. So that's why it's quite important to try to reproduce different pathological scenarios so that we can actually provide them as cohorts and populations within our platform. Some of the work that we have also done in a while, for quite a while, is working on the prosthetic valves, for example, where we solve, here it's with an inverse boundary method to solve the valve motion and to try to characterize and also validate some of these fluid mechanics after that. Actually, there's some work but it's currently in revision, where we're validating the simulations against measure data in patients, where you can actually characterize and actually reproduce some of the blood flow mechanics after valve implants. Now, also very interestingly, you can actually calculate different markers so that you can actually quantify the potential thrombogenesis of a prosthetic valve, or how it actually affects the positioning of that valve and on the flow and this thrombogenic risk. So it's quite interesting to try to use all of these different models to address even different parts of the cardiovascular system, but hopefully someday they might come together to solve a big single, full heart single simulation. Now, of course, that will require a lot of computational power, but it depends if there is a good use for that specific problem. It could try to be, we're trying to address it and go in that direction. Now, of course, many of these models, you want to try to personalize them. And we have patented a methodology to try to actually extract cardiac fibers from cine MRI. Because generally what you needed to do is to obtain diffusion tensor MRI. But the problem is that in vivo as well, you may not get that much of resolution to be able to capture the actual fiber orientations. So we have created different methodologies to be able to estimate those fiber orientations from the MRI. So this is something we have been, specifically Jose Maria Pozo has been working within ELEM, and we're hoping to use some of these methodologies to create even more personalization, not only looking at the anatomy, the electrophysiology, the ECG. But also going a little bit onto the tissue characteristics and the tissue characteristics in terms of the fiber orientation. So that will be very exciting to use in patients. Now, I wanted to talk a bit more on female and male sex differences, because this is something that only recently has been tackled a little bit more in the literature. Generally, all of our models have been done with, a generic cell model. Basically, it's neither a male nor a female, or it's, a mix in between, or is, just an average from the cells that you can measure in the lab. And in terms of the pathologies or how the cardiovascular risk occurs in males and females, we know it's different. And so we want to try to address that within our simulations. We want to try to create, more distinct populations where you can actually label them as a male or as a female, and try to observe what are the specific properties that make the cardiac risk of males and females different. And if there is any way to try to understand and try to address that in the clinic or in a with a specific therapy, to try to understand what all of that comes from. And of course, that's quite complex. So one of the things that we started with was to look at the anatomical differences and the approximate cell model differences, what they would produce within our simulations. The one thing we were addressing in this paper as well, this was published a couple of years ago, trying to understand, as I mentioned before, what are the differences from our simulations when you actually have a smoothed heart in comparison to how the heart actually really looks like, with all of their trabeculae and papillaries. So this is a study where we try to understand a little bit about that. Why? Because it is very important, to know what are your assumptions when you're creating a model, and how your assumptions may impact your outcome or your, the results from that model. We know it is a fact. We cannot capture this amount of detail right now, at least currently with some of the techniques that we're using. We cannot capture it for every single patient. So we want to understand if that would be of a big impact in terms of our predictions regarding that specific patient. So we chose this is a male heart, this is a child heart actually, and two female hearts. These are all a normal, anatomically normal, perfectly normal hearts. So we have the detailed version and the smoothed version of each one of those hearts. So we know that male hearts are generally larger in size. And we do know that QT interval values of females, I guess you might be, you know what the QT interval value. So just very briefly, the QT interval value, it refers to the ECG. So in the ECG, you have the first QRS wave that refers to the activation of the heart. And then there is a T wave that refers mostly to the repolarization of the heart. So if you look at the time between the start of the activation of the Q wave and the end of that T wave, that tells you approximately, that is the QT interval value, that tells you approximately for how long your heart has a voltage gradient inside it. So it is actively, it says electrophysiology is actively changing that gradient. So we do know that those QT interval values in females are generally longer. So here we're just characterizing the ventricles that we have for both the detailed and the smoothed hearts, and by looking at the difference between these smoothed and detailed hearts, we can extract this trabecular volume of each one of the hearts to actually see whether any of the characteristics that we observe inside our simulation may be related to, approximately related to that trabecular volume. We're also characterizing the false tendons. These are really interesting structures that are very thin, very, very thin tissue sections, or, long, thin tendons that connect one side to the cavity to the other. So they're basically, shortcut electrical fibers. So they are highly useful actually to establish a very synchronous activation in the heart. So we're characterizing how many of those they have. You can have several long false tendons or less. it really depends in the anatomy, characterizing some of the wall thicknesses, and these are just the mesh elements, the millions of elements for each mesh. Because, of course, for these electrophysiology meshes, you need very high resolution electrophysiology meshes to actually capture some of those fast dynamics in the voltage. So we applied some of sex differences within our cell models to be solving those hearts. These come from a publication from Yang and Clancy, Colin Clancy, where they characterize the effects of hormones, both male and female testosterone, estrogen, and progesterone, on male or female cells. And what they observed, of course, there is a prolongation of the action potential dilation in females. This is the endocardial and the epicardial. They did not provide data from the mid cell. So for that study, we actually kept the mid cell as equal equal for both males and females, because there was no really data available on that, but we'll see. Now, of course, you can obtain different pseudo ECG markers. Here, we are not solving for the full torso. What we did was actually locate the hearts into a torso, and then observe all of the coordinates at which we would be putting the different leads for a 12-lead ECG. And we compute the pseudo ECG in relation to those coordinates in those torsos. So we can obtain different things like QRS duration, QT or QTC duration, peak calcium integral. Here, what we do is just have an integral of the entire calcium transient that it would give you a little bit of a relationship to what the mechanics would be doing. Because these simulations were mostly electrophysiology. So we applied exact same tissue diffusion properties to all of our hearts. So we have the exact same exact same tissue properties. We have 2 different cell models, and we have 4 different anatomies. So each one of these goes for one of the anatomies, because we wanted to try to understand what makes a male heart or a female heart. Is it the anatomy? Is it the cell dynamics? How much of that part role plays on each one of the models? So here we also looked at the detailed. Let me hide this. Oops, sorry. Here we also looked at the detail effect of the detail and smoothed geometries, and this is just in a regular heartbeat for all of our hearts. Now you can see when you look at the detailed and the smoothed geometry that it's the dotted line are the smoothed, and the other one is the detailed. You can see small differences, mostly on the magnitude of the waves. Here, for example, there's a larger difference in terms of the actual upstroke of the Q wave, because these also depend on each of the different false tendons or endocardial structures that are that are in each of the models, right? So definitely there were differences in terms of the magnitude. Again, here we're talking about hearts that potentially have a smaller volume, just because you take out all of the tendons. So potentially that's That's why you may see a smaller gradient. You have smaller volume, and since we're using just the pseudo ECG, we can capture everything with that. One thing that was very interesting is that with the detailed hearts, many times we saw fractionations of the QRS, these little wiggles on the QRS, which many times weren't so apparent on the smoothed hearts. That was quite interesting. But of course, when you have the trabeculae, there are different pathways where the voltage is traveling. So there are gradients that are more visible in that sense within our simulations than with a smoothed anatomy. So things that you would expect. Sorry, and just to mention, of course, the female phenotypes had longer QT intervals in all the different hearts. That was to be expected as compared to males. Now we wanted to go more in detail. I wanted to see whether the QRS interval duration could be related to approximate, for example, the trabecular volume. Say if you have a large amount of trabeculae, would that speed up your QRS, for example, or would it slow it down? But there was not real correlation. This is the QRS interval duration, and this is the trabecular volume in green for each one of the hearts. So the heart with the highest trabecular volume, it really didn't have the highest QRS interval. Neither was this one wasn't either the lowest trabecular volume, and yet it had a higher QRS. So it really depends on the arrangement potentially of these trabeculae rather on their volume. We looked at the left ventricular thickness. We would expect that a thicker heart would have a larger QRS. In the case of our simulations, you can see that, here, the left ventricular thickness is in purple, not in green. You can see that with a large thickness, you didn't really get the higher QRS. It was not a matter of the thickness of the ventricle that was more or less related to that QRS. So, okay, let's see if the bigger the heart, you have a longer QRS with the myocardial volume now in red. So the bigger heart, what is the male heart, this one, it also didn't really have the longest QRS. It was not dependent on that. Now, of course, these are 4 hearts. We have the exact same, tissue properties. And we observed that actually the existence of these trabeculae are actually, modifying this. By the way, here, oops, sorry, and I didn't add that. Sorry. So there is no real correlation in this aspect. In terms of the QT interval, it happened very much the same. We expected perhaps if they're highly connected, there's high trabecular volume, they may potentially either repolarize faster or, repolarize, the slowest, really, because we didn't know exactly what to expect. And there's also not a lot of correlation. With high trabecular volume, we did not obtain neither the longest QT, neither the smallest. Same again with both the myocardial volume and the left ventricular wall thickness. So what we observed from this is that it's not as simple. When you try to make assumptions on what you would expect with these models. So the next thing that we did, we wanted to try to see what would happen in terms of our predictions of ventricular tachycardia. And in that case, it's like, what if a male and a female had the exact same infarct? So again, we can use this exact same heart and put an infarct and model it with a male or a female cell model. Let's see what would be the different risks for ventricular tachycardia. So we did a program stimulation protocol. So, we do different pacings to try to find where the ventricular tachycardia and to trigger that ventricular tachycardia. One of the very interesting things about this, what we found, is that here we're reporting the number of events. That means every time my simulation was giving a reentry, even if it was 1 or 2 beats. We considered a sustained VT as 3 or more reentries. But anything that I was looking that was creating a reentry, I recorded it as an event. So what we actually observed here are the total events for 3 different stimulus locations of the program stimulation protocol. So this is a protocol that is used clinically to actually detect the ventricular tachycardia. So what we observed is that the males, here are the differences between the details and the smoothed ones. I'll mostly focus on the detailed ones. In the males, we had so many more instances of a reentry than for the females, and it's quite notorious. Like here, if we were, and this is exactly the same scar and exactly the same heart. If we were activating from the right ventricular outflow tract here, we had seven reentries for the males and none for the female. That was quite interesting. And the number is just quite strikingly different. Now, of course, we cannot extrapolate this to everything that you observe in the clinic, but because it's one heart and it's a completely idealized scenario. But in the clinic, many times the females have a worse prognosis in terms of ventricular tachycardia than males, mostly because they basically, for example, they don't get treated that much as males. And so my question here was like, well, why aren't females getting the treatment that they require? Is that because, people in the clinic are sexist? I probably don't think so. Not everywhere. Is that because you may be going for a treatment, but you are not having as many symptoms. You're not having as many tachycardia as men. While men may have more instances of that tachycardia than you do. So, very interestingly, this is the tachycardia of that female, and the female had very few instances of reentry. However, when it appeared, when we found the tachycardia, it just never stopped. It just basically continued on and on and on. So it was potentially more lethal in that sense. A tachycardia that does not stop on its own, it's potentially deadly. So here on the right, I was estimating or looking at all of the reentry points created by the simulation. And there were plenty, and they just went on and on and on. Here, this reentry point here in blue, it's the only one that was exactly the same one as in my smoothed version of the tachycardia. So this is in my detailed heart, and this is in the smoothed heart. So we found a tachycardia here. It reproduced 3 cycles. It stopped. But the only single reentry point that coincided with the tachycardia with the trabeculae was this one in blue. So, we may be able to capture some of those reentry locations with our simulations, but definitely not everything, definitely not all. And they may be actually different to what you would expect if you were, modeling it with the full trabeculae. Now, this is my simulation of the male. Here again, we found the tachycardia, but again, it just after 3 cycles, it just self-terminated. While the locations of these reentry points were completely different to the female, of course, and this point in blue was the only one that was actually the same location as in the other smoothed versions that I'm going to show you in a second. So here we obtained one tachycardia that actually also continued quite a bit, but the reentry locations, but this one did not continue. It self-terminated in a few cycles. Here we have this one is the same point as in the detailed case. These green ones actually coincided with another stimuli location of this same smoothed version of the heart, but these red ones are different from this heart than from this one. So yes, whenever you are stimulating from different locations, you may have different reentry points. But when you are stimulating from different with different smoothness, you may also be getting different reentry points than if you had with the full trabeculae. So what we came up with, what we understood from this was that even in this case, the exact same infarct could be lethal for a female, but not for the male. The male had more recurrences of BT, but it was not sustained. So the reentry locations were completely different between sexes, given the same infarct morphology. And these differences were solely observed from the cardiomyocyte ion channel differences between male and female, nothing else. But of course, there are like all of other different variations that will happen between males and females, daily variations, circadian variations that were not, of course, not assessed here. So we're trying to put this into use for some of the things that we are producing within ELEM. So we have been applying some of these models for male, female in the highly detailed anatomies to assess cardiac safety of drugs. So what we do and this is part of our platform that we have produced, we have these highly detailed human hearts. We have male and female phenotypes for these hearts, and we can to apply drugs into them. The drug effect is observed by introducing the IC50s, the characteristic of the drugs of how they block ion channel within our cell model, and we compute this in a population, and we can actually quantify the concentration QT prolongation. This is at how much concentration of a drug does my QT prolong? Because QT prolong, if a drug produces a large QT prolongation, it is a potentially very arrhythmic drug. So you want to try to identify that very early, not to have it fail afterwards. So that is what we have been doing, and this is part of our V.HEART-SAFETY platform. Where we actually create populations. We have male hearts, female hearts with their own phenotypes, and we can create ion channel variability of conductances within these hearts to actually produce a range of differences or changes within that same heart, that they are completely plausible as observed by clinical data. So we create these changes as long as we have normal, in this case of normal cohort, normal QRS, and normal QT values. So to actually reproduce just a spectrum within normality to have this normal population. We can create male and female populations, and we can run full virtual trials. There are other things that we have been adding into our models that we can include a little bit age, mostly in terms of approximate hormonal concentrations in blood, average hormonal concentrations in blood on both males, mostly in males, because that's where testosterone values change significantly with age. In case of females, we look at different menstrual cycles, electrolyte imbalances, or many things like that. You can include pathologies. Everything that I've shown you before can be more or less well included within the creation of a virtual population for this platform. And we want to produce that to create, to test drug effects. So this is one of our main, I would say, products right now. That is this V.HEART-SAFETY platform, where it's your own virtual CRO. You can log in, you can select your cohort or your population. You can input any drug properties that you want, and you can obtain the QT interval prolongations of that drug. So we want to try to extend our methodologies to try to cover the full range of the entire pipeline for drug development. So when you're looking at drug discovery, you want to try to test loads of molecules and try to discard them if they are unsafe. When you're going more, if they pass some of these initial tests and you're going more in towards, the market, then you may try to focus a little bit more on, trying to see whether they work or not for a certain population, or want to try to, provide a more robust evidence. So that's why we have created two different platforms. The V.HEART trials, the one that I showed you a bit before, well, I'll show you a bit now, that involves the solution of the 3D problem on different hearts with different characteristics. And this is V.HEART Discovery, where we have employed AI technologies to try to provide a fast solution that has been trained with full 3D cohorts. I'll explain a little bit more of that. So these V.HEART trials goes more for preclinical and clinical, where you can create your population, look at the drug effect, look at the pseudo ECG, see how much their QT changes, analyze those markers, and try to determine how toxic, how cardiotoxic could that drug be. we have tested this with many compounds. These were some of the first compounds that we tested, where in gray you see the clinical data, and in blue you see the results from our technologies. Here on Dancetron was the one that gave us is slightly more different than the other drugs, more outside of the confidence intervals. But there are different aspects as well of the data from drugs that might have been the cause for this. But anyway, I will not have time to talk a lot about that. So when you create a drug, a clinical trial, you generally have a placebo group, which we did not have in these simulations. In these simulations, you have a baseline simulation of each one of our hearts with their QT interval, and then you apply the drug, and then you look at the difference of the QT after the drug. In the next simulations that we did is that there is a placebo always. And when you look at the clinical data, here it's in gray. When you look at here are the points of the placebo are here at the zero concentration. So that is how much the QT is changing with zero concentration of a drug in a clinical trial. You can see that dispersion is massive. And you can see also in the clinical trial, the dispersion of the QTs are gigantic, right? But it is very striking that with a baseline placebo effect like this, you can actually observe a correlation with the data, no? But, it's in terms of computationally, how could we try to reproduce that? Because in the end, what you observe in the clinical trial is the delta QT. So it's the corrected QT after also taking into account the placebo, which is the first delta that you have. So for that, what we did is employ the same methodology, but now actually introducing within the same trial different stages of menstrual cycle, for example, where we know there are different QT intervals, different stages of age in males, for example, where the testosterone is more markedly changed. And we applied some kind of circadian rhythm by looking at the approximate average changes throughout the day of hormone levels in that occur normally. Normally, our hormone levels change throughout the day, so we took that into account to create a morning, afternoon, and an evening QT. And of course, we have we apply this population scenario, and after doing that, what we actually observed is that the computational trial here you don't see that much because it's behind the red points. The computational trial actually achieved about half of the overall placebo QT interval differences, prolongations observed in this placebo branch. And it also added some of the variability within our model. The nice thing is that most of the results were actually well preserved after doing all of these changes within our model. So it was quite robust in that sense. Interestingly, there was a paper where they published a statistical model for a placebo. So we applied that placebo statistical model also to our computational trial to see how it corrected it. And it is here in red. So you can see that, of course, there are more effects on the placebo than there are, of course, that what we were looking at with just looking at hormones. But it was very interesting that statistical model actually corrected quite well our simulation in terms of the clinical data. So, the placebo has many other aspects to it, but we can try to approximate them with some of the methodologies that we've been testing.
Yes. I don't want to interrupt you, but
oh yes,
yes.
I'm going very slow. Yes.
So
I will,
if
yeah,
we want to leave some minutes for discussion.
absolutely. Sorry about that. Yes. So this we have talked about. Let me just go a little bit further. This we have talked about. So again, the key idea is that we want to see what those effects are done also in pathology, because all of the drugs that are produced, they don't only go to just normal healthy humans, because of course that's not the purpose of them. So we want to know what those effects are in pathology. So these are some of the things that we have done. So the nice thing about some of these methodologies as well in 3D is that you can observe the actual arrhythmias, which is, one of the key features. And well, I will have to go very quickly through this. Now, the last thing is that some of these simulations, what you can produce is all of these, methods where you can tackle industrial interests from different points of view, which is quite interesting, and which that's where we want to go. So I think that's where I will stop now to have more time.